Section 9.5 is concerned with a topic called the kinetic molecular theory. And the kinetic molecular theory describes how the temperature of a gas is related to its total energy and also to how fast the gas particles are moving. So it puts a little bit more detail into things than what we get from Graham's law of effusion and diffusion. Now, we probably have some thoughts already about how the energy of a gas is related to its temperature, and the energy of a gas we probably would recognize is going to increase as the temperature goes up. And we've also probably thought a little bit about how the velocity of our gas particles is going to increase with temperature as well. And we're going to say that what we call the root mean squared velocity, which is a measure of the average velocity, it's almost the same as the average velocity, that is going to also increase as the temperature goes up. And from our discussion previously of Graham's law, we know that if we're at fixed t, what we would expect is that root mean squared velocity decreases as our particles get heavier and their molar mass goes up. So we already have a kind of a gut feeling for how these things are related. Now we're just going to put a little bit more detail on that and actually give you some formulas. So the kinetic molecular theory of gases can actually be used to mathematically derive the ideal gas law, and it's based around 5 main assumptions. The first assumption is that compared to the size of the container, the volume of the gas particles themselves is negligible. And so what that means is that the volume that the gas has to move in is just exactly the same as the volume of our container. We're going to be making the assumption that our gases move in what we call rapid random motion. So they're just moving around without thought, they're colliding with one another, they're colliding with the container walls, they're moving around rapidly and randomly, not in any particular direction. The third point is kind of interesting. The energy associated with the movement of the gas particles, or what we call the kinetic energy of our gas, is determined by one thing and one thing only, and that is its temperature. And we mentioned this previously, as the temperature goes up, we're expecting that the energy associated with movement, the kinetic energy, will also increase. So this is interesting because what we're saying is if we keep if the constant temperature means constant energy, regardless of what else is occurring. Okay, this is interesting. We mentioned that the gas molecules are going to collide with one another, but they're also going to collide with their container walls. And what we're going to assume in developing the kinetic molecular theory of gases is that all collisions are what we call elastic. So if we have two cars colliding, right, boom, all movement will stop. The kinetic energy will change a lot. There will be no more energy associated with movement. All of that energy will get converted into sound and light and the deformation of the cars. The cars will become squished. So all of the kinetic energy will disappear. The cars will stop moving. That's a classic inelastic collision. In an elastic collision, the kinetic energy remains constant. So this is more like kind of bouncing, a really bouncy ball off a wall. It hits the wall and then it goes bang, shooting back with just as much energy, right? So when collisions are elastic, the kinetic energy remains constant. The particles just bounce off one another. If one particle does slow down, another must speed up to keep that energy constant. The fifth assumption of the kinetic molecular theory is that there are no forces of either attraction or repulsion between the gas particles. The gas particles are acting like the other gas particles aren't there. Okay, so if we make all these assumptions, then we can do this thing, we can do a bunch of math that gives us the kinetic molecular theory of gases, and we can actually use that to ultimately, if we wanted to, derive the ideal gas law from first principles. So a key idea will be that at a given temperature, the kinetic energy for a gas will be constant. However, there's going to be a distribution of speeds of the particles. So the speed that we're going to be calculating is this thing called the root mean squared speed. We've already talked about it a little bit. It's it's related to the average speed of our gas particles. It's a little quicker, but as the root mean squared speed goes up, our average speed goes up. But the important thing is that we see a distribution of speeds. Very few particles are, barely moving. Very few particles are going super fast. The most likely speed is right at the top of this peak here. And then we see that we have more particles that are going a little bit faster than the most probable speed. And then we have, less than half of our particles are going slower than our most probable speed. So that's why the average is a little bit quicker than our most probable speed. Okay, so this is called a Boltzmann distribution, this type of curve here, and it was figured out by Ludwig Boltzmann. So we're going to be doing some math on this guy. So it can be shown that the root mean squared speed is the speed of a gas particle that has average kinetic energy. Right? And the average kinetic energy, and you might know the formula from a physics class for kinetic energy, is going to be 1/2 times the mass of our gas particle times by the root mean squared speed squared. But what's also important to know is that the average kinetic energy is also equal to 3/2 multiplied by the ideal gas constant times by the temperature in degrees or in Kelvin units. Now, it is important that R, when we use this expression, is expressed in base units of the SI system. So that's going to be kilograms meters squared, seconds squared, moles per unit Kelvin. So this is slightly different, or is a very different value from if we express R in units of liters atmosphere per mole per degree Kelvin. So we do need to be aware about that whenever we're doing stuff with speeds or with energies. We're going to use R with these units. So anytime we're using R in a formula with anything concerning energy or the velocity, we have to use the 8.314 value. It's also because of the way that the base units work, and you've learned a little bit about this already, the molar mass in this formula has to be given in kilograms per mole. So we have to use base units. And so the molar masses that we calculate either online or through using a periodic table, we're going to have to divide those by 1,000 to get them in kilograms per mole. So I've reorganized these two expressions to get an expression just for the root mean squared velocity, and here it is. The root mean squared velocity is equal to the square root of 3RT on your molar mass. And so what you see there is that the root mean squared velocity increases as the temperature increases, and the root mean squared velocity will decrease as the molar mass increases. So it reflects our kind of intuition that we had before about how the speed of our particles should be affected by molar mass and temperature. Okay, so here's a classic example. It says calculate the root mean square speed of neon atoms. I can look up the molar mass of neon in the periodic table at the temperature at which their average kinetic energy is 5.18 kilojoules per mole. So I want to be aware that I've got kilojoules here, so I'm going to turn that into joules per mole just by replacing the kilojoules with its decimal multiplier, with its multiplier with its power of 10. Okay, so the mass of 1 mole of neon atoms, it's 0.0218 kilograms, and I know that because when I look up the molar mass of neon on the periodic table, 21.8 grams per mole. Got to divide that by 1,000. So here's my expression relating kinetic energy and root mean squared velocity. And I've given this value here, 5.18 by 10 to the 3. So I'm going to reorganize and get an expression for the root mean squared velocity, or the root mean squared speed, and then I just put all my numbers in. Like I said, I'm being aware that I had to turn that from kilojoules into joules, and then that I had to give my molar mass in kilograms, right? Otherwise I'm going to get the wrong answer. Now I cancel out all of my units and I'm left with correct units for speed, which is meters per second. And this is pretty cool. At this, under these particular conditions, these guys are like going fast, almost 700 meters per second. That's almost, half a mile per second. That's really, really, really quick. So these gas particles are, they're hustling, right? They're moving around pretty darn fast. Okay, so that's an example where we were using the kinetic energy and the molar mass to calculate the root mean squared speed. We can also use the temperature to help us do these calculations. We have this formula, and I recommend you write these formulas down on a piece of paper and keep them handy for your quizzes and tests and so forth, or you can kind of like start a document and put them in there. But we're going to use this guy from one of our very early slides, and we were given our temperature and we're given our molecule. So our molar mass here is 32.0 grams per mole, but we just got to remember to divide that by 1,000 to get it in kilograms per mole. That's important. And then other than that, we'll look like we're ready to go. We've already got our temperature in Kelvin, so we just got to make sure to use our correct value for R with the proper units that we want, and then away we go. So 3RT on the molar mass, take the square root of that, and you can see that these oxygen molecules, they're moving 482 meters per second at room temperature. So like I said, these guys are hustling, and if you heat it up, it would go faster, and it would increase its speed quite rapidly. Okay, so that's how we sort of use the formulas, so in a myriad of kinds of ways. So I hope that's helpful. So let's have a look at this a little closer and see if we can kind of extract some more meaning out of it. So we know that the root mean squared speed is what we call directly proportional to the square root of the temperature. So what that means is that these guys are related like this. If everything else is constant, if I multiply the square root of the temperature by some number x, I will multiply the root mean squared speed by some number x. And then it also says here that what we're saying is everything else is constant, then the root mean squared speed will be inversely proportional to the square root of the molar mass. And then that just means this. That if I multiply the square root of the molar mass by x, then I will multiply the root mean squared speed by 1 on x. That's really what that means, okay? So, you can kind of keep that in mind, but what it means is as the mass goes up, if everything else is constant, root mean squared speed goes down. And as temperature goes up, if everything else is kept constant, root mean squared speed will also go up. Okay, so this tells us that heavier gases will have lower speeds with a narrower speed distribution at a given temperature. So these are looking at the noble gases, and they're all at the same temperature. I think it was 298 K. You could do the math if you wanted to. And you can see that the helium, which is right at the top, because it goes helium, neon, argon, xenon, and then I think the last one, krypton, and then there might be even be radon after that. But what we can see is that they get heavier and slower, but also the distribution gets narrower, right? So the heaviest has the slowest average speed, or the slowest most probable speed, but it has the narrowest distribution, and then the lightest gas has the broadest distribution of speeds, but it has the fastest, most probable speed. So you can distinguish the gases on the basis of that speed. If you had a long tube full of a mixture of these guys, and you just put a little hole in there, you would expect the helium to come out first, right? Then next out would be the neon, then the argon, and then the xenon, and you could actually use this as a means to separate these gases, and I mentioned previously we do this all the time. Now, when we consider our formula for root mean squared speed, it's also telling us that as temperature increases, the average speed of the particles increases and our distribution will become broader. So if you have two samples of gas with the same molar mass, the one that's at a higher temperature, on average, the particles will be moving quicker, but there'll be a broader distribution of the speeds. As you cool that sample of gas down, the particles will slow down and the distribution of speeds will become narrower. So sometimes this will, you'll be presented with a series of curves and you'll have to interpret them in terms of either mass or temperature. So it says the following curve depicts the speed distributions for the samples of 1 mole of gas at 0, 1000 and 2000 degrees Celsius, and you have to decide what belongs to what. So really the important thing here is just not to get confused. As the temperature decreases, the root mean squared speed will decrease. So that guy's going to be 0, that one's going to be 1000, and this one's going to be 2000. It's really just kind of like taking your time and not making a mistake with these kinds of questions where it's concerning labeling the curves. Okay. So that concludes the section on kinetic molecular theory. I hope you found it helpful.